Hello students, this lecture is about kinetic molecular theory. Kinetic means motion, molecular means referring to molecules, so we're going to be looking at some things about the motion of molecules, and a theory is an explanation of some things that we observe in nature. So basically what we're going to do is see what we can explain by looking at the motion of molecules. Specifically, our objectives are to explain how temperature and pressure are the result of molecular motion. We're going to see where these two things come from, and we're going to be able to explain why thermal energy always flows from hot to cold. We've learned in previous lectures that heat always flows from hot to cold, and we never really talked about why, and now we're going to be able to see why that is when we look at the motion of molecules. Our third objective is to understand the connection between molecular motion and what are called the phases of matter. And you probably already know about those: solid, liquid, and gas. And we'll take a look at another fourth form called plasma and tie it all together, again using molecular motion. So I think step one is going to be to define what kinetic molecular theory is. And kinetic molecular theory is an idea that the overall behavior of matter, and what we mean by this is things like temperature and pressure and density and other properties that we know about matter. These properties can be explained by looking at what individual molecules are doing. So the theory says we can zoom in way far in and look at what the molecules of a substance are doing and explain these bigger picture behaviors. And if we look at what's going on at a molecular level, this is a great little video that shows what's happening at a molecular level between two gases here. So I'm pretending I have a gas over here. Here's a thermometer. It shows that this gas is at a high temperature. So you can guess that these molecules are going to be moving very quickly. They're going to have high kinetic energy. And I have another gas over here in this chamber on the right, and it's at a lower temperature. You can see the thermometer right here is low. So these molecules are not going to be moving as quickly as the ones on the left. What I have in the middle is we're pretending that this is a wall or some kind of membrane that when molecules from one side hit it, they can transfer their motion to the molecules on the other side. And what's going to happen is that these molecules are going to be moving much faster than these molecules, and overall they're going to start pushing on this wall a little bit more than these molecules will, and we'll see what happens. So let's press play. You can see the molecules on the left are moving much faster than those on the right, but gradually as they hit the wall over time, some of their kinetic energy is transferred over to the right hand side. Because on average, that wall is getting hit more often by particles on the left-hand side than it is by particles on the right-hand side. So on the whole, this motion of particles is drifting towards the right. And eventually, you can see that they even each other out. We're almost at the same temperature right now, and both sides of the gas are moving at about the same speed by the time we get to the end. So this is an example of what's happening in thermal diffusion at a molecular level. Let's play it one more time so we can see it. Hot is on the left, cool is on the right, and you can see gradually over time, heat, which is the transfer of thermal energy, is going from hot to cold because, on average, the molecules on the left are going to be colliding more than those on the right. And this sort of motion, these collisions, drift towards the right over time. Until gradually, here we are at the condition of equal temperatures, molecules moving about the same speed on average, and that condition is called thermal equilibrium, which we learned about in a previous lecture. So here's a static image, just a frozen image of what's going on. Here's the high temperatures. There's more collisions happening from this side than this side, so on the whole, everybody kind of drifts this way towards thermal equilibrium. And heat transfer is going to be from hot to cold. So we can start defining some things about the overall behavior of matter based on what individual molecules are doing. We already know this. Temperature measures the average kinetic energy of the molecules. Kinetic energy means the energy of motion, so temperature is sort of measuring how much motion do molecules have in a substance. But we're going to add to that this idea called pressure. Pressure is how hard the molecules are hitting the walls of the container. And you can think about how we use pressure for things like water. If we say a high pressure hose, there's a lot of water flowing out, the molecules are going to be hitting pretty hard. We could think about high amount of pressure inside of a tire, like a car tire. If it's high pressure, the tire is very stiff because molecules inside are pushing outward pretty hard. If the tire has low pressure, then the tire is very soft. You can poke it and bend it because molecules on the inside are not pushing out on the walls of the container as hard. So that's physically what pressure is. And now we know from looking at the motion of individual molecules that heat is going to transfer thermal energy from hot to cold because, on average, molecules are going to get hit by other molecules harder and more often from the hotter side, just because they're moving faster. And this is one of the key insights of KMT, of kinetic molecular theory, that we can actually provide an explanation for why heat is always going to flow from hot to cold and not the other way around. So now that we know a little bit about what is happening at the molecular level inside of matter, we can start talking about phases of matter and grouping them by how those molecules behave. So as far as we know so far, we can group matter into 4 states. We call them states of matter, sometimes we call them phases of matter, and we classify matter based on the motion and structure of molecules. So we say, okay, this group of things, the molecules are moving in this particular way, we're going to give it a name. And that's going to be one of the states of matter. So the first state of matter, molecules are generally not moving around, but they are vibrating. Remember, molecules don't ever fully stop except at absolute zero temperature. So for a normal solid, molecules are vibrating and jiggling around, but they're not moving in general. And a solid object is very hard to expand or compress. It's going to have a fairly rigid shape relative to the other states of matter, and we can classify this based on their molecules. The next state of matter, we're going to go up a little bit more in motion. Molecules can move, but they generally stay together and slide over each other. This is still something that's pretty hard to expand or compress, and a liquid also has the property that it takes the shape of its container. Because these molecules can kind of move around a little bit, a liquid can change its shape much more easily than a solid can. And you can see that increased motion has already happened, going from solid to liquid. So liquids are going to occur at higher temperatures than solids for a particular substance. Next, we have a gas. Molecules are now moving independently. They're no longer stuck to each other. They're no longer having to stick together as much. They can actually just sort of fly around on their own. And this makes gases very easy to expand or compress. And gases are just going to expand to fill whatever container they are in. If you think about a water bottle or some kind of bucket or bottle or container of some kind, and if we were to fill that with a liquid, let's say I'll fill it up with water, and if I have half the amount of liquid that's going to fill up this container, it's only going to fill up half of that bottle. It's going to stay in the bottom half. It's not going to fill up the whole container. That's a liquid. If I were to take that same container and fill it up with a gas, the gas is not just going to stay down here at the bottom. The gas is actually going to fill up the entire container. So let me give myself a little bit of a thicker line so I can fill it up little bit faster. But the gas is going to take up the whole container. It's going to expand to fill up that entire thing. And even though there may be the same amount of matter in both of these containers, it's just the gas is sort of spread out more to fill up that entire container. So that's a unique property of gases. And then finally, a plasma is a gas where there's so much kinetic energy, there's so much energy of the particles that they actually can't get any more kinetic energy, and we have to start removing electrons to give the energy someplace to go. And that gas now becomes electrically charged, and we call it a plasma. And if we look at these four states of matter: solid, liquid, gas, and plasma. Let me give myself a thicker arrow here. As we go from solid to plasma, we are increasing the temperature because we have to increase the amount of molecular motion to go from one to the next. Okay, we're making molecules move faster when we go to solid to liquid, so we have to increase its temperature to increase the kinetic energy. And then when we go to gas, we got to increase the temperature some more. And when we go to a plasma, we have to increase the temperature to a much, much higher degree. We are going to talk about how matter changes phase, how it goes from solid to liquid to gas to plasma and back again in a different lecture. Right now we're just defining what these four states of matter are, some general properties about these states of matter so that we can identify them. And then later on we'll start exploring what these things really mean in detail. And in class we'll see some examples and work with some examples ourselves of each of these things. Incidentally, the most common form of matter in the universe is plasma, as far as we know, at least what we've been able to confirm as distinct matter. But most stars, all stars in the galaxy are made up of plasma, which is a very exceedingly hot gas that's undergoing nuclear fusion, and that makes plasma the most common form of matter in the universe. Let's go back to our objectives. You should be able to explain how temperature and pressure arise from molecular motion. That is, how does temperature relate to molecular motion? How do we get temperature from the motion of molecules? How do we get pressure from the motion of molecules? You should be able to explain why thermal energy always flows from hot to cold and not the other way around. And finally, you should be able to understand the connection between molecular motion and phases of matter. If I give you a phase of matter or a state of matter, can you tell me what's going on with the molecules in that substance when it's in that state?